So with this problem, we want to focus on the Faraday's law and apply the concept that can be used with your right hand, which we usually call the right hand rule, but it's also known as the direction of the curly electric field. Um, and it's defined as the association with time of varying magnetic field. Faraday's law is a quantitative relationship between the rate change of the magnetic field and the curly electric field, which kind of covers the basics. So, with this problem, the direction of the magnetic field line force is typically always away from the North Pole and toward the South Pole of a bar magnet. And the magnitude of the magnetic field is just basically depends on the density of the magnetic field line. So, for part A, they're just asking us to find the direction of B as the instant of time. And in order for us to do that, for this case, the magnetic is basically placed in a way that the axis passes through the y-axis, and at the given time, it passes through the y-axis. So the direction of the magnetic field at the origin, at instant time, is towards the south pole of the magnet, which means it's a negative y direction. For part B, we want to know when the bar magnet is still underneath the origin but closer to it. So the magnet is placed in such a way that the axis passes through the y axis at the given instant of time. And since it does, the direction of the magnetic field at the origin at the instant of time, which is wrote out as T sub 2, is also towards the south pole of the magnet. And it follows the same thing as A, which means it's in the negative y direction. Part C wants us to find the magnitude of the magnetic field larger at time. So, the magnitude of the magnetic field, due to the bar that is inversely proportional to the distance of the bar magnet, we can just try. Basically, it's time instant. The magnitude of the magnetic field is larger at the time instant, T2, since the distance of the magnet is small. That's what I would think. So, part D asks us what's the direction of delta B, the vector change in the magnetic field from T1 to T2. So, it also goes in the negative y direction. Basically, like the direction of the change field, which is delta B, is in the same direction of the magnetic field. So, it's also in the negative y direction. Part E is what is the direction of the So, the direction of the negative rate of change of the magnetic field is the opposite. It's going to be the opposite direction of the change in magnetic field, which is going to be negative d over b over dt, which is in the positive y direction. G is asking us what the direction is of E at the location 1, 0, 0. And did I skip one? For F, is the pattern curly electric field clockwise or counterclockwise? And it's going to be clockwise. Like, we can find this out from Lenz's rule, and it's not a non-column electric field, so it would drive current in the direction of make the given magnetic field and attempt to give the flux constant. And since it is given that the magnetic is moving towards the origin, it causes that magnetic field to increase. So increasing magnetic field causes the pattern to curly non-column field, which will be clockwise. So going back to G, it asks us for what is the direction of E at the location 1 and 1. And that would be a positive Z direction. And that's because the electric line of force gives the direction of the electric field at the given point. So because of that, the direction of the electric field is in the direction of the tangent. And using your right hand rule at point 100, you get that it's going in the positive Z direction.